Welcome to the course imdb Data Management. In this lecture we will talk about the join operation. First we will talk about what is actually a join operation. The join operation combines tuples from different tables. There are two general categories of a join, which is an outer join and an inner join. The standard version of that is the inner join. In an inner join we combine tuples from both tables only if the join predicate matches. In the outer join, we combine the tuples also if the join attribute doesn't match. In that case, if we have a tuple on the left side and no match on the right side, we just fill up the values with null. There are also two furthermore specializations of the join operation, for example the equijoin and the semijoin. They are discussed in more detail in the text in the book, but we won't go deep into that right now. Joins are usually used in normalized relational databases to combine tuples from different tables. We have different kinds of joins. For example, there is a one-to-one join, which means, or one-to-one relationship. This means that for one tuple on the left side, we have exactly one tuple on the other side. Another kind is the one-to-n join, or relationship. Here we have one tuple on the left side and multiple matching tuples for that one tuple from the left side on the right side. An n-to-m join means that we can have for multiple tuples on the left side, one or more tuples on the right side, and vice versa. The m-to-n join is usually done using an additional table that basically stands in the middle of the two tables. We will talk in detail about join execution for main memory databases that use dictionary compression and compression and dictionary encoding. Our main goal here is to leverage the sequential scan speed of modern CPUs, to leverage the caching effects of modern CPUs, and to avoid random lookups. Also, we want to avoid every early materialization and materialize as late as possible during the join operation. In our example here, we have two different kinds of a join. One is the hash join, and one is the sort merge join. The query example that we will use for our two join operations, or for two different implementations of the join operation, will be the following. We ask what is the population density for the cities in the state of Hessen, which is a state in Germany. We have two tables for that. We have the well-known world population table, and we have another table, the locations table, that has the information of how large in square kilometers is a state or is a city. You can see the SQL query just down below. To the hash join, we have one basic requirement for the hash join, which is a so-called hash function. A hash function takes any input and maps that input to a 64-bit integer. So no matter how long the input is or what the input is, the same input will always be mapped to one single 64-bit integer. The hash join works in two phases. The first phase is the hash phase, and the second is the probe phase. Starting with the hash phase. You can see here the two tables that we are trying to join. We have the world population table with the column city, and we have a locations table, again with the column city. The first step that we do right now is to apply all the filters that we can apply upfront to the join operation, because the join is a comparatively expensive operation, so we want to keep the result set that goes into the join as small as possible. So we will apply the filter for the state of Hessen first, and then continue with the join operation. In that case, we have a list of tuple IDs which represent the tuples that are cities in Hessen. In the second phase, we're going to try to build up the hash map. Here we take the positions of all the cities in Hessen, take the value ID of the city, and hash that value ID to our table, to our hash map, as you can see here on the slide. With that mapping structure, we now start with the second phase, the probe phase. Here we scan sequentially, which is fast on modern CPUs, over our larger relation. For each value now in this larger relation, we look into the mapping structure to find the corresponding value ID of the first relation. And with that value ID, we do the hash function and look up the hash value in the hash structure for that key. If we do not find in our hashing structure, if we do not find the key here, that means that there is no matching tuple in the other relation. That either means for the inner join that we do not have tuples to emit to the result, or if we have an outer join, we know that we now have to fill the other side with nulls. So the result of the probe phase is basically a list of tuples with the position of the left tuple combined with the matching tuple of the right relation. In the last step of the hash join phase, we simply have to materialize the results. So we take both positions from the two tables, materialize their results, combine them, and emit them to the user. The second implementation of a join operation that we want to talk about is the sort merge join. We have a certain problem with the hash join, which is that we have, depending on our hash function, that we might have collisions. That means that two different input values might map to the same hash key. In that case, for every time we apply the hashing function, we have to deal with collisions. Another implementation of the join operation is the sort merge join, which does not have this hashing function, and thus we don't have to care about collisions. The sort merge join is usually slower than a hash join, but still it's interesting for us to show you that join. The algorithm usually basically works as follows. In the first step, again, we filter the locations tables with all the predicates we can apply up front to the join operation. Second, we create a list of cities and the corresponding value IDs, and create furthermore a list of unique value IDs of the cities and sort it. Third step, similar to the hash join, is building a mapping structure, mapping the two columns from the different tables. And the fourth step is to create a list similar to step 2 for the other table, followed by the last step, which is basically the merge. So here again you see the two tables that we're trying to merge now, and on the right side you can see the dictionaries for both tables. And again, as we have said, the first phase is to apply the first filter, which is only cities of the state of Hessen. So we already have reduced our input for the join on the left for the smaller relation. And you can see the resulting list on the left, which says position 902, position 912, and so on are cities in Hessen. With that input list, we now create a list of pairs. Each pair consists of the position, so the position in the left table, and its value ID. This list is going to be sorted by value ID, so that in the first position you have the lowest value ID of the list, and the last position has the item with the highest value ID. Furthermore, we also create a list of distinct value IDs. This list of distinct value IDs is used to create our mapping structure. It's similar to the hash function. We have to map values from two different tables because we cannot ensure that the dictionaries are going to look exactly the same, or that the sorting order of both dictionaries has to be the same. In our example, we will deal with the problem that there is no matching tuple for Darmstadt, which has the value ID of 37. As you can see here, we couldn't find in the mapping structure a matching value for Darmstadt in the other table. So we just put in not available in the table. Before we can start the second phase, we have to ensure that we use our mapping structure to have the same value IDs mapped to each other. We will do this by appending the new value ID from the right relation to our list of tuples which we have created using the left relation. So now we have a list which has, again, a list which has a position of a tuple from the left relation, its old value ID, and the new value ID which we map to. Before we can start with the second phase, we're going to sort that list by the new value IDs. Here you can see the actual merging phase, which is the join, basically. Since both input relations are now sorted by value ID, and we know that each value represents the same value, each value ID represents the same value, we can just scan sequentially over both relations and emit all the resulting joint tuples. To conclude, we have the question, so what joint algorithm should I choose? This highly depends on multiple factors, but one important factor is the size of your relations that you're going to join. If you have really small relations, there's another join implementation, which is the nested loop join. This is really well suited for small relations, but it's rather slow for large relations. The hash join is one of the fastest join implementations, but there are also cases where the sort merge join is really fast. For example, when the columns are already sorted. So columns don't have to be sorted up from the join operation. I can immediately start with mapping and joining. There are some problems, as we have mentioned. The join operation has to deal with collisions, so we have to think about these collisions. And the join operation also suffers if you have two really large tables. So my hash mapping, my hash structure is still going to be quite large, and in my probing phase I'm going to have a lot of cache misses because of that. Thank you.